the stage is yours.
All right. Thank you very much, Una.
Yep.
Very nice introduction. Like Una mentioned, my name is Daniel Russo, a last-minute replacement for this lecture, so please be gentle with me. I've been working at IRENA for the last year or so in the Power System Transformation Unit, and what we do is basically conduct studies to support countries in devising pathways to power system transformation to more renewable energy. A little background about myself. Before working here, I was working in a consulting firm, did energy research in the UK, and then came here after doing a master's in environmental policy. So what are we going to talk about today? Like Una mentioned, it's power system transformation and planning for that, the actual planning process. And the kind of structure that we'll be working with is first I'll discuss the main drivers behind this transformation process, what it actually looks like when we look at different country transitions. And then my colleague Francisco, who deals more with the engineering side of things and operational side of power systems, he'll go into some more detail on those aspects, and especially how solar and wind, which are variable sources of power, affect the whole planning process that we'll talk about. So we can jump right into it. First thing, like I mentioned, what are the drivers behind what we call this power system transformation? And broadly, there are two main ones. The first is the overall agenda to decarbonize the energy system and avoid dangerous climate change, reduce our emissions levels from the energy sector. And this is probably maybe a good place to distinguish the energy sector from the power sector. Energy as a whole can be used for transport, heating, and power, so the electricity delivered to this room, for example. And so what we'll focus on today is the power sector part of that. And then maybe the next big driver is the reducing cost of specifically solar and wind generation. So the electricity generation from those two sources the cost of that has been falling really rapidly over the last decade. And so that's the second driver that we'll discuss. This figure and slide might be familiar if you were here 2 weeks ago. The director of our program was here and he presented this as well. What it basically shows is a broad view of what has to be done behind the agenda to decarbonize the energy sector. In the UN Conference of Parties, the 21st meeting in Paris in 2015, there was a global agreement to reduce the increase of emissions to prevent a rise in temperature from pre-industrial levels to below 2 degrees Celsius. And what that implies for the way that we conduct our electricity system and our energy system now is that we essentially have a budget over the next century, to 2000 to 2100, of gigatons of carbon dioxide emissions from the energy sector. And it happens to be, depending on your assumptions, somewhere around 800 until 2100. And as part of the agreement, countries established their own commitments. They're called nationally determined contributions to how they would reduce their own emissions. And if you look at what we'd have to do, the sort of budget envelope of what we can emit from the energy system and what the country's commitments are, the sort of overall budget, if you followed the country commitments, would be totally exhausted by around 2050 already. So there's a lot more work to be done in terms of country commitments to improve sort of their policies and actions to reduce emissions. And this is based on IRENA's work around decarbonization of the energy system. What you see is kind of what you would need to do from different areas to reduce the energy intensity, the carbon intensity of energy. And so that's the amount of carbon dioxide emitted per unit of energy that we use. And if you take these goals seriously, you'd have to reduce that by somewhere in the order of 85% between now and 2050. And what IRENA's study has found is that almost 50% of that can be done by introducing renewable energy cost effectively into power systems. And then if you consider taking some of the renewable energy and using that for the other sectors I discussed, like transport or heating, that would give you another 15% of the reduction that's required. So clearly renewable energy is being pushed by this agenda. I mean, it's one of the main drivers to decarbonize. And it's going to be further incorporated into country commitments, we hope, as meetings continue to take place. And here's a picture of what those commitments look like over the last decade or so, and how they've changed. And so they've luckily been strengthening over the last decade. In 2005, 43 countries had renewable energy targets for their energy sector. But if you look at 10 years up to now, that's changed to about 164 countries have some sort of commitment to renewable energy in their policies. We may have to take one of them and change it. The United States may turn to what Canada looks like there, where it's sub-national targets that could be implemented. But this kind of is a good segue into the next big driver, which is it's not only sort of an international political movement that's been driven by the need to decarbonize and avoid climate change, dangerous climate change, but it's also a major push from the cost side of these technologies. And what this slide shows is kind of how the costs of renewable technologies have changed over the last 7 years. So if you look at the bottom here, you'll see this is prices, costs of renewable energy. This is per kilowatt hour that they generate, what you'd have to pay to get their generation in 2010 and 2016. And the size of these bubbles is the size of an individual project that's been built. And all of this data comes from IRENA's Renewable Energy Cost Database, which has thousands of projects that have been built in the past. And so we can track exactly how these costs have declined. And maybe what's the most noticeable here is how solar, right in the middle, photovoltaic technology has decreased from 2010 on average to 2016. And then also how low this onshore wind cost has become over the last 6 years. This band of 10 here is the cost of traditional fossil fuel powered generation. So how much gas-powered or coal-powered plant would cost to run and provide electricity. And so what you see is that in the last few years, these two technologies, particularly solar and wind, have come down to the point where they're competitive with what have been traditional power generation technologies in the past. And so this is a major driver because not only do you have to make your policies based on certain environmental targets, but you have to consider the affordability of your energy system as well. And so if we look a little bit more closely at those two specific technologies which have changed so rapidly over the last years, this is the picture of what are called power purchase agreements, which is the price that sort of a government or anyone wishing to buy energy would pay from solar PV in orange and onshore wind in blue since 2008, how that's changed, how private developers and operators of these technologies have lowered their costs, essentially, of providing this energy. And so you can see, if you look all the way to the bottom, that just recently, especially for solar PV, we've seen costs that are much lower than traditionally even fossil fuels have been over the last century or so. So this is one of the main drivers, is that not only do we have sort of a political movement, but we have economic forces that are causing countries to realize this is beneficial on a cost basis. And so when you take these two things together, you get something that really transforms not just kind of the cost of a system, but really everything about it, how you would plan it and how it's structured. And this is a picture of Germany, the German power system. And what you see is in the yellow and red, wind and photovoltaic plants. And this is kind of to show a change in how power systems have generally been structured from a centralized large-scale plant to really thousands of smaller distributed plants. And you can see in the year 2000, so 20 years ago, there were about 30,000 small-scale wind farms, inland farms and things like this. And that's changed to over 1.5 million wind and solar PV plants spread across Germany. This is a major change in how you plan for something like this and how you distribute energy to customers. And it's not only in Germany or well-off countries in Western Europe like Denmark, even though they were the first kind of big movers into this. You have it taking place in small island states as well, which are leading the movement now. This is an example of the island of it's Upolu in Samoa. And this island on the left, it's home to about 80% of the island's population. And they've tried to transform now their system, which relied on kind of costly diesel generation, which was necessarily imported, to generation that's now more diversified across hydropower, wind, and solar. On the other side, we have another smaller island, which is in South Australia, and Tasmania, King Island. And this is a country that's now almost entirely able to run on solar PV, wind, and storage solutions, which is something we haven't really seen in the past. So even, small island states are leading a lot of this movement themselves under some pretty difficult conditions. So this is a picture of sort of what's been driving it, what we've seen happen in different areas, and maybe we can look at now where it's going in the future. And so this is a trend that we see is set to continue. If you look at what this picture is the investment in power generation capacity over the last 20 years or so, a little bit less than that. And what you can see is that the additions here, every year here, is the amount of new capacity added per year. Capacity is here on the left-hand side. And this is the share of the new capacity every year. So that's represented by this green line. And so what you can see now is since about 2012, over 50% of all the new capacity that's been built in the world has been renewable energy capacity. And if you look more recently at 2015, 2016, almost 50% alone is from wind and solar power. So these two generation technologies that are really reducing rapidly in cost, you can see a clear impact on what people are investing in and what they're building their power systems with. And I think if you want to make the distinction between sort of capacity and generation, which Francisco will discuss a little bit more later in the presentation, around 25% of all global power generation is now renewable, and this is something that's growing by about more or less 1% every year. And so looking into the future, how does this picture look? You can see that this is kind of a picture of specifically wind and solar power, which we call variable renewable energy, and short for that is VRE share. And so these are the two, like we saw before, technologies where costs are coming down rapidly and investments are increasing at the same time. And maybe when you only looked a few years ago in 2015, these shares in total generation of countries' power system were around 5, often less than 5%, so not really making much of a contribution. But based on work that Irina's done, analysis that we've done, by 2030, it's expected that this share of only these two sources, wind and solar, would increase to orders such as 30%, 50%, even in some advanced countries. And so this signifies really a major shift in the type of sources that are providing power to countries. and it has impact on the actual way that you plan your power system. And this isn't something that previously could be kind of taken in a simplistic way, but with these new sources coming online, you have to think about how they would affect your power system in ways you hadn't had to deal with previously. And so before we discuss that, we can talk about what exactly we mean by energy planning and power system planning. This is kind of a look at what we're planning for. So if we're talking about planning a power system, what exactly do we want to get out of that? And commonly you refer to it as the energy trilemma, which is you want stable and reliable power, so deliver power when it's needed. You want it to be affordable, so lowest cost that you could possibly receive the power. And then you want it to have low impact on the environment. So it would be reliable, affordable, and clean power, essentially. And so this feeds into different dimensions of who the stakeholders in planning a power system are. So on the technical side, ensuring you have a reliable system, there are transmission system operators, distribution system operators, and the planning offices of a government. On the affordability side, you have to sort of run economic studies in perhaps different offices of a government or different private actors. And on the environmental side, there are policies and regulations which could occur in even a different portion of the government itself. And then overall, in terms of integrating these aspects, this creates new challenges. So secure operation, what your investments are required, and sort of how your market is structured. All of these things could potentially change with the introduction of these new sources of power generation. And so at IRENA, what we do, we have sort of a team that focuses specifically on this transformation of the power system, the introduction of a lot more solar and wind technology. And it's made up of about 4 pillars. What we have on one side is market, design, and regulation. We recently released a report on adapting your market design, so how exactly you procure energy to power transport fuel and electricity systems if you have more of these variable renewable energies, like wind and solar. And then the 3 other pillars, so outside of the policy and market design, is long-term, near-term, mid-term, and near-term studies. So what we do under these 3 groups is we take economic models and technical models and help countries to plan optimal pathways along this transition, to look and assess different scenarios where maybe prices are higher or lower, or demand for electricity is higher or lower. And we've recently released a report on the long-term side of things, where I work, which is about integrating these variable renewable sources in the planning process, as well as the modeling that you have to do to see what your energy system could look like, say, 30 years from now. So this report covers a lot of the methodologies and sort of the steps that you need to make sure that you would take if you're planning an energy system or a power system, if you think that you'll have a higher share of these new technologies like wind and solar PV. And since this is more of where myself and Asami work, I can discuss this a little bit more. And then on the medium term and shorter term studies, which is where Francisco works, he can elaborate a bit more on those. And so when we talk about long-term planning of an energy system, what exactly do we mean? If you want to think about it in one way, it's mainly to do with investment. So investing in the infrastructure that will provide your power generation is something that's inherently a long-term thing. Once you plan for this, it could take years to build up your planning process and generate the construction, so it's a long-term planning process. But it's also kind of a long-term impact once you have say, a plant in place. They could last for 10, 20, even up to 50 years for hydro and nuclear plants. And so what we talk about when we talk about long-term planning is how to structure that investment in the lowest cost way under a certain framework. And when we talk about it for power systems, it's also termed generation expansion, which is simply just the power generation infrastructure expansion over the next 20 to 40 years or so. And this sort of planning happens under a few different conditions. It happens in compliance with long-term policy goals. So those policy goals around affordability, environmental sustainability, maybe even diversifying your energy mix from different sources. It also feeds into political consensus making and the stability of your investment environment. So if you have different parties who have different views on how the energy system and the power system should be developed, then this process can act as a way to coalesce those groups and have them agree on certain pathways. And it's also often linked with the non-power sector planning. So the other energy sectors I mentioned, there's transport and heat. Often you have to plan those in conjunction just to make sure that you're not missing something that would affect one or the other in the process. And this is typically done in different government departments or institutions, public institutions. For example, here we have different examples. The Philippines has a Department of Energy which conducts a long-term energy plan, a long-term power sector plan. A regulatory commission is often the institution that performs this as well. A utility or a specialized agency. And so this can really differ from different countries, one to the other. And just to show that there are real people that work on this, this was a meeting that we recently had in Argentina, which gathered South American energy planners to discuss the inclusion of solar and wind into their power systems. It gathered representatives from 10 different countries, and there were about 50 people that were there to discuss how they're dealing with this issue right now. But if you went back into the countries themselves, there would be hundreds of people working in the institutions on precisely this long-term investment issue for their power system. And these are some examples of the actual documents that they produce. Each of these countries has sort of a long-term energy plan where they take economic models and technical models and try to think about how their power system could develop over the next 20, 40 years, all the way up to 2050, to comply with the policies that they've put in place. And one important note is that it's not only to ensure that they're complying with current policies and making sure that current goals are met, but in our discussions with the planners in South America, what we found is that one of the main points of this process, this long-term power system planning, is to actually form the basis to develop new policies. So to explore different options. And what you see here is Colombia, Brazil, Argentina, and Uruguay. What they use this long-term plan for, deciding which infrastructure they'd like to build, is to design policies to support different technologies and to provide sort of a stability for investment needs, if they'd like. And one other important thing to note in the long-term planning process is that the scope of the planning can also change from country to country. So it's not only about power for certain countries, but they'll plan their power and their heat and transport all together in a single process through a single document. And as well, the planning horizon could differ by country. So certain countries plan, for example, 10 years ahead in Argentina, Bolivia. Certain countries have a longer term horizon, all the way out to 2050. And this really depends on sort of the historical institutional setup that countries have, what sort of resources they rely on, and how often they're able to sort of collaborate with other departments around these things. And another place where we work, particularly here at ARENA in Bonn, is planning long-term power systems in an African context. And this becomes additionally interesting because not only do the institutions in certain countries still have a certain way to develop in incorporating renewable energy, some of them have only, for example, looked at oil and gas for the last few decades, and they're just starting to think about these things now. But the demand for power is also increasing really rapidly in this context, and that has a lot of different implications for the planning process. And the main thing that you'd like to look at here is to avoid the costly investment mistakes, where if you're not planning 20 to 40 years ahead, you could build something that would really not be worthwhile down the road. And what we have here is just a look at sort of the more detailed steps in a planning process. And this is now where Francisco might be able to step in and give us some more information about how beyond the generation expansion planning, in things like geospatial planning, which is the planning of your transmission network to distribute the power generation, dispatch simulation, and technical network studies. So these are more related to shorter term technical issues, how you go about the planning process with new sources such as wind and solar. And so I can maybe hand it over to Francisco now. You can take us through that.
Thank you, Daniel, and maybe a short break just to introduce myself. And first of all, thank you for being here and give us this space to discuss with you. My name is Francisco Guevara. I come originally from Colombia, but have spent like more than 10 years in total here in Germany, trying to learn something about these things. I'm an electrical engineer from background and have worked before ARENA in the industry with the system operators and planners in my country and with wind turbine and product developers here in Germany. I'm going to take over the presentation that Daniel started, and I'm going to try to discuss a little bit about the characteristics of these new generation resources, or not new anymore, but different, which are wind and solar, and why we started to speak about challenges and differences and being careful about planning. So this is what I'm going to try to do. In the first part, I'm going to talk about the long-term planning or the investment in generation, which aspects which differentiate the wind and the solar from the traditional generation are or need to be taken into account, and why. And later, I will discuss a little bit about what are the challenges for the people that is operating the power system, for the people that is right now making sure that we have lights, we have computers working and all these things, and why with wind and with solar, we started to talk about challenges and what has happened in the meantime. So first of all, maybe a little bit about some characteristics of the variable renewables is that so they depend on weather conditions. So wind and solar will only generate power when we have wind blowing and sun shining, no? Different than a coal power plant or a nuclear power plant that they will generate if I have fuel. The other thing is that as they represent an investment, the investor will like to put them in the place where I have the best resources. This may differ a little bit from the conventional generation that can be placed in locations which may be more convenient for the consumers because they are closer. So let's say that so these two characteristics, the one constrains the availability of the energy, and the other one is more the location, which may require from the people in charge of providing us with electricity to develop also the transmission or the distribution networks. And the other thing, which sounds a little bit weird, non-synchronous, what does it mean? It means that for 100 years, the generation of power was based on one physical principle, which is called synchronous machines or synchronous generation. And this is like a big thing that is spinning. And this is spinning because I'm burning fuel or using a nuclear reactor, so the heat of a nuclear reactor, and it makes like this big mass to start to rotate. And with this rotation, I'm producing electricity. And this rotation, I'm putting electricity behaves like a magnet that is putting an opposite force to this rotation. And the whole power system and the whole network and all what we saw until 15 years ago was based on this physical principle, and it was really analyzed and studied, and the people in charge of providing us power understood that this is very complex, but they understood it relatively well, and we were able to manage to have systems that work this way. And everything was adapted and developed in that direction. But then suddenly we came with new generation sources that physically are different, and then we are introducing a change in something that was working and that took decades to be developed. And this also represented a challenge. I'm going to speak later about not only the challenge but also the solutions, because we have been like in this revolution of the renewable energies already for more than a decade, so a lot has been learned and a lot has been achieved, and what was before a challenge is now more something that needs to be taken into account when planning the system. But the message is, so physically the wind and the solar are different, so this is something that people in charge must be aware and must take care of. Now, when discussing about the characteristics themselves and the influence in this long-term investment, so first thing is this availability of resources that depends on climate conditions. Here is an illustration. So the blue plot is how the demand for electricity behaves in 3 different days in a country. Specifically, this is the country of Ireland. So here we have the late night and early morning hours. This axis is the demand for electricity, so it is very low. Then is the morning and the load starts to increase because people is waking up and going to work. And here, let's say after 8 a.m., people is in the offices and is working, so it is much higher than here at the late night. So here the working journey ends, so the electricity goes down, but then people go home and they cook, they turn on the lights, they watch TV, whatever, and then we have a peak in the demand. And more or less this behavior is consistent through different days, so very low, late at night, high in the evenings. And here this orange plot is the wind generation profile. The wind didn't wait to the people to go home to start blowing. So it just, during these first 2 days, there was almost no wind, so the production of wind power was very low. And then suddenly the wind started to blow, so the production of wind power increased, and this peak of production coincides with the lowest part in the consumption curve. So it means that differently than the other conventional generation, I don't have the resources when I need it. And in terms of challenge or things that the persons planning a power system have to consider is that, this is the thing to take into account, that the resources that now I'm installing are not going to be available all the time. And consequence, this is a result of an analysis that the group of Asami and Daniel did, is that maybe for supplying the same amount of demand of electricity, which is these two columns here, I will need, with the case where I focus on more variable renewables, I will need to install more capacity. So we call, like, reference is a case where I consider a small amount of variable renewables in my plan, and renewable energy target is a case or a scenario for the future. In this case, is for 2030, if I'm not wrong. Yeah, where I'm trying to plan or to estimate how much capacity or power I will need to install in my system to cover this same demand. So, and this is the reference case. So I will need this amount, 60 gigawatts. And in the renewable energy target, I will need to install a little bit more. Why? Because I don't have the availability of the resources all the time. But I am also having an influence on the way that I use the available generation resources. This gray part here is natural gas production used to cover the demand. Here is the power that I installed, so where I invested money and the generation that I built. And here is how I use these resources. And of course, in the reference case where I have less renewable energy, then I have to use more gas power or thermal power, let's say, in general, which is the one that is available most of the time, as long as I have fuel and the machines are working. And this amount is reduced in the case of the renewables. And this has then the whole implications on really on the cost of operating the system. Of course, it's better if I have to use less fuel, and in terms of CO2 emissions. This is just an example from Denmark on how this issue of not having the power that is needed all the time can be handled, thinking in the long term, and is to interconnect with the neighbors. If I share, I mean, I don't know, in life it's always better to share, and in this case it's the same. No? If I am concentrated in this space and I have these generation resources that may be too few when I need, or maybe a lot when I don't need them, then if I can interconnect and share, or better trade with my neighbors, then it can be that I can receive renewable energy when I don't have it, and I can export it when I have it. And this is a way, like, to help to deal with this challenge in the long term, to think about interconnecting and trading the electricity. Another issue that is associated with this long-term planning, or that the people that is thinking about preparing a system for 10 years should think about, is that is related to this non-synchronous issue. So as mentioned before, for almost a century, the power network was developed based on the physical characteristics of the conventional generators. So still, in large systems, there are limits to the amounts of renewables or variable renewables that I can put. This is not the case anymore in the small islands, but in a large system like the whole Europe, or even a country in South America, it is still very challenged to reach and to go beyond a certain point. So if I'm thinking like in an optimal configuration of my electricity mix in 10 years, this is something that I may think about, that I may, at a certain point today, with state-of-the-art technologies, I may have to limit this amount of renewable that I will be able to have working in my system. This is just more discussing about this issue of stability, which is related to how robust a system is to all the changes and all the disturbances that it can receive, if I can say that, during a normal day. And this has to do with this physical characteristic that I commented before. Another challenge or difference that we have to consider when planning a power system with a lot of variable renewable is the variability. We saw it in the first picture that we have the production of the wind was low and flat, and then very quickly in a few hours it started to increase. And if I need to keep a balance all the time between the power that I produce and the power that I consume, I will talk about this a little bit later, but it's important to consider that with the electricity, I always, like the amount that I consume must be produced instantaneously. It's difficult to store it. So I need to have, and if I have renewables and they increase their production very quickly, then I need to have the rest of the system must be able to handle these variations. And then this is why we talk about variability and ways to handle this. Again, when thinking about long-term planning, but also like in the short term, is to think about larger geographical areas, because those changes that we see in the production of the solar or the wind are more steep or more pronounced in smaller areas. Like for example, if we take a single wind turbine and we start to see like every minute how much power it is producing, depending on the wind speed, we will see that it changes a lot, but it's incredibly crazy. Then if we look at the wind farm that has 50 wind turbines, this change will be proportionally much slower. And if we look at the whole region, like the whole north of Germany, then the variation will be smoother. And if we look at the whole Germany or the whole Europe, this variation will be reduced. So if I'm thinking long term and I'm planning long term, I may think about this issue, and then I may think about ways to enable to, again, have a bigger geographical area where I can trade or I don't know if share is an appropriate word, because in this life, I mean, everything has a value, so I don't share, but I trade electricity with other countries or with other regions, and this helped me to smooth this issue. This plot shows what I was talking before. So here is 15 turbines, they change a lot, and if I have 200 turbines, then the change is smoother. And like the people that talk about power systems and power systems planning and operation and renewables, they talk a lot about flexibility. Flexibility is like the ability or the capacity of the power system to adapt itself to these changing conditions on available power. So if I have like my electricity network in Germany, and I have 20 megawatts of wind, and in 1 hour I have 20, and then in the next hour I have 15, a flexible system like this is able to manage this by changing the habits of the consumers, but mainly those days is by changing the outputs of the conventional generators that are there. So let's say flexibility is the capacity to adapt the system to the changing conditions in terms of available power that the variable renewables impose. Until now, most of this has been taken care, or let's say the conventional generation has taken care of this, so it has to be flexible. But as the more I put renewables in my system, the more I have to think about it, and in the long term, then I have to think that I need also to develop not only my wind and my solar, but I also have to take care on how I develop the rest of the generation, so the conventional generation, so that it is flexible enough to increase or decrease the power to be able to maintain this balance between what I produce and what I consume. And flexible, when we talk about flexible generation, conventional generation, we don't talk only about how fast they can increase or reduce the power that they produce, but we also talk about how fast can I turn this generator on and put it online to produce electricity, and how much, what is the minimum generation that they can handle. So because most or a lot of generators, they have to work at a certain point, let's say like working at 75% of the power that they can produce, like to work well. Maybe they cannot go below that. And this also affects the flexibility of the system, because it means I have only room between 75 and 100% to go up and down, responding to the changes of the wind and the sun. But if my generators allow me to go down, then again I have more flexibility. And this picture here shows exactly this effect of the loading or minimum load of the generators. Here up is, let's say, like this light blue represents the minimum power that this conventional generator has to generate. It means that if I'm going to cover the demand is the red one, which I am covering it with this type of generator that has a minimum value, this type of generation, which is still conventional but doesn't have this restriction, and renewables. There's a minimum amount or a minimum amount of the energy share that I have to give to this generation, because otherwise it will not work or it will get damaged. And it means that if I have a lot of renewable energy or wind and solar, I have to cut it and waste it or curtail it, as we call it, to guarantee that the conventional generation is working at the secure levels. And here is the same picture, and so these black spots here are the amount of wind and solar power that I cannot use, because these constraints that are imposed by my thermal generation. Here in this case, we have like the same demand and same amount of available wind and solar, but we simulated, or they simulated, the persons that produced this plot, with a more flexible generation in terms of the minimum power that they must to produce without having problems. So here we have like 21 gigawatts, and here it was 10, and then the black spots, which are the wind and the solar that I cannot take, is smaller. So here is just a summary of what we, basically when we talk about flexible generation, so then we talk about being able to increase and decrease the power rapidly, being able to operate or being more tolerant when working at lower loading levels. It means like not to have to generate always between 75 or 100, but maybe to go lower to 50 or 20%, and also to be able to start quickly. And those are kind of seems to be very technical, no? Like, the flexibility, the startup times, but this is so important for the long term that there are even like policy initiatives like this Clean Energy Ministerial that is starting campaigns to create this awareness and to also to generate mechanisms that incentivize the development of flexible systems. So, and this reminds me again one of the slides from Daniel, that he showed like the challenge is not only a technical challenge, but it is associated with the policy and it is associated with the economics. No, we have a technical challenge, and we identify the problem, we identify the solutions, but then we need the mechanisms to allow the solutions, and this shows this link, and let's say that this is an aspect that is touching like this long-term planning. Another characteristics or characteristics, sorry, of the renewables that, or the variable renewables that we were talking before, is the location, the constraint in the locations. If I am investing money in a wind generator, I want to put it where the wind blows so that I can produce electricity and I can get money. And this not necessarily coincides with the locations where the load is. This is a map of the Dominican Republic, a country in the Caribbean, where we currently are doing a study. And here we show like these orange areas is where the people lives, and the industry, where the industry is located, so where the electricity consumption is. And the blue areas are where the good resources for wind power are located. And it results that even the best place is this part, which is really far away. And of course, before, they developed the electricity network, not considering the wind. So the infrastructure that we have to transport power from here to here is not the strongest. So the people thinking about long term and thinking about developing like these areas, they also may think about how to develop the infrastructure to be able to transport the power from here to here. And this is, again, another characteristic of the variable renewables that has to be taken into account when thinking in long term, in order to guarantee that things work properly, that I make better use of my resources, and that the lights keep on. This is just an example of issues that may arise related to planning, when all these things are not taken into consideration. So this is an example in China, where the average of wind power that must be curtailed means that is available but cannot be taken or consumed because of these constraints in the system, is 17%, which is higher than the average worldwide. It's important to take into consideration that even in Germany or in Denmark, still some level of curtailment is necessary, because systems are not yet ready to have 100%, but those amounts are really non-significant. But in this case, this is a relevant amount, and especially considering that the amount of wind power is not very big, and the issue may be, or the root of this issue may be found in this planning, that all these aspects that were discussed before were not considered. Just very briefly, I don't know if there is any question, or do you want to comment anything up to this point?
I have a question. What
Yes.
do you mean with the curtailment? Energy, 70%, or
Energy.
power?
Energy. Mhm. It's clear, like, this concept of energy and power is somehow strange, but when I talk always about like the demands, the amount of power that is consumed, or the shares of renewables, it is usually energy, which is what counts for money mostly. And power is what is installed. So, for example, if I see a coal or the nuclear power plants here outside, I can say, yeah, this is a power plant with 400 megawatts, then I'm talking about power. But this plant, if it works every day, every hour, it produces this 400 megawatts times 24 hours, and then it produces an amount in megawatt hours.
Yeah, and you mentioned stability. Do you consider voltage, annual, and frequency stability, or only frequency stability?
Exactly when you mean that? When?
Because you mentioned stability, that there are many stability problems.
Yeah.
But I know that there are, for example, 3 stability problems.
Uh-huh.
I think that you mean frequency stability.
Not necessarily.
Annual
Uh-huh.
and voltage stability as well.
Yeah. No, it's the I mean, this is a combination. I mean, this is kind of a complex thing, but this separation is something that the researchers and the people in the practice has done to easily identify the problems. But when talking about renewables, okay, let's say that the first thing that happens is the frequency, because it's related to this balance and to this quick reaction of the system to this lack of balance. But you cannot say it's only frequency, because what happens is that you are changing, physically you are changing the system, and then the system is going to react differently to any perturbation that it may have. When I say perturbation, is that whenever a tree falls into a power line, or whenever a light strikes, or whenever for any reason one generator disconnects, this is what I mean with disturbance or perturbance. And the power systems are planned to be robust to many of these things. And initially they were planned to be robust based on this physical principle of the conventional machines. Now, physically, I'm changing this. So the way it reacts, it's going to be different. So now, if a tree falls into a line and then it makes a short circuit, probably the reaction of the system will be different than 20 years ago with the same demand, because physically the system looks different. And this may involve also voltage stability and angle stability and frequency stability. For easy thinking, maybe the first thing is the frequency, but I can talk a little bit more about this now. I'm talking about the technical constraints. Let's say that before we were talking about what I have to consider when planning a system in the long term. So, I am a person that I'm in charge of the policy of the country, and I want the best future for the world, and I'm committed with climate change, and I want to have this mix of renewables. But then I have to consider those aspects that were discussed before to develop long-term strategies. But we also have to consider that the power system, so the electricity network, is something that all the time is changing. And so in order for us to have electricity right now, there is a lot of people working there in a control center, monitoring the system, and making sure that everything is fine, and taking the appropriate measures if something happens. Like, for example, if one of these big lines breaks, or the tree thing, whatever can happen. And also, behind these people, there are big teams of engineers working and doing technical analysis and calculations, just to make sure that what the operators are receiving right now is the most accurate information, and that they can take the better decisions. When I used to work for the transmission system operator in my country, they used to make the analogy of operating the system with operating an airport. So you have the people in the control center of the airport, like controlling the traffic. But the work is not only that. I mean, behind those guys, there were a lot of people doing before and in different horizons of time calculations and preparations, so that the persons that sit there, they can only focus on what they have to do and on taking the best decisions. And I'm going to talk very briefly, maybe to repeat a little bit of what was discussed before, but then going faster, and how these characteristics of the renewables challenge this operation of the power system. So this is a conventional power system like 15 years ago. So I have the production of the power, which was centralized with nuclear or with coal power plants, and then this power was transported close to the customers through the transmission networks, which are these high voltage networks that we see, like these big towers with these cables. If we make an analogy with any other product, I don't know, like chocolates, this is the factory of the chocolates, and those are the motorways where the big trucks are transporting the chocolates to the cities. And then in the cities, the transmission networks, they deliver the electricity to the distributors of electricity. So those were basically, in the analogy of the chocolates, like the distribution networks for my product. Here is, for example, like the Stadtwerke Bonn. They received at a certain point from these big highways, and then they distribute the power to the consumers, and finally we have the consumers, and the power was flowing this way. And then, as mentioned before, we are transforming this, and we are physically transforming this because we are introducing these generators that are physically different, and we are also putting power generation here in the distribution and even power generation here at the homes or at the factories. And this is, as I mentioned before, a physical change. And if we start right now to think about strictly on the technical side, just to mention, before I was talking more like this strategic long-term planning, but now it's maybe to think more about technically what happened is that I changed the system physically. And if I am the operator of the system, I need to guarantee that I deliver you the electricity at the best possible cost, so at the lowest possible cost, and that I keep the lights on. And in order to make this happen, there are some preconditions. So precondition number one is that I have power all the time to cover the demand. Remember that different than the chocolates, I cannot store a lot of electricity in a warehouse. I just produce it, I transport it immediately at the speed of light, and I consume it. So I need to have power, I need to have a network and the correct infrastructure to deliver this power from wherever it is produced to wherever it is consumed. I need to have these resources or this flexibility to balance all the time, and I need to be stable, or let's say to be robust. It is nobody wants a power system that there's a storm and then there's a light strike and then the lights are off. I mean, this world of today cannot afford this. So this must be stable and reliable. And those are the preconditions. And as mentioned before, the renewables are physically changing the system, and therefore they are physically changing or impacting these conditions. I don't want to stop too much into the next two slides, probably they are too technical, but this is just to show again the issue with the balance of the power, that here is what I consume and here is what I produce, and this is like a balance, and I always need to have the same amount, because otherwise there's a parameter in the network which is called the frequency, will move up or down to levels that are not acceptable or can be dangerous for the system itself. So the system operator must guarantee that the frequency is within a certain level, so must maintain this balance. The other thing is the voltage. So whenever we connect or we plug our computer, the voltage is like this force that pushes the electricity to go in and to make things work. And the voltage, all the equipment is designed for a certain voltage. If the voltage is too high, I burn the equipment. If the voltage is too low, the equipment doesn't work. So the system operator, in order to keep the lights on, must guarantee that the voltage is within certain limits or within certain levels. And again, he planned it and he developed the system based on the physical principle of the synchronous generator and this physical principle of producing power centralized, transporting, distributing, and delivering to the customers. And now we are changing this order, and this may affect also like this necessary condition for a good supply of electricity. This slide, I also don't want to spend too much time because it's repeating what we were discussing when talking about long term, is that the renewable energies have different properties. So one is that it is not synchronous. The second one is so it affects this reaction of the system, and then it affects the stability, and the stability is reflected in the voltage and in the frequency. let's say that in many systems, especially in the smaller ones, the first thing that pops up is the frequency stability, because it's related to the balance of the power and to the size of the system. And this is maybe why we always think about frequency stability when talking about stability and renewables, maybe to try to answer your question. Also, we talk about uncertainty, that was what we were discussing before, that we don't exactly know if the wind is going to blow when I need it. And despite the fact that we are improving and improving, how can we forecast the amount of wind power that we will have? It is very difficult to have 100% accuracy. So I will always need to have some extra means to manage this balance between the power that I produce and the power that I consume. Then we have this variability, so this characteristic of variability that was what was discussed before, so that the power that I produce with the wind and with the sun can change. And then as one of the preconditions for my system to work properly is to maintain this balance between what I produce and what I consume, and to be able to handle these variations, so then the variable renewables may impact this. And the third one is the location and the modularity. And let's say that all these aspects we discussed quite long, how they did affect this long-term strategic planning, but they also affect the daily operation. So the people that is there sitting in the control center right now operating the system, they must take into account these issues, and they have to take decisions to handle whatever happens with the system based on the solutions that the people that prepare them to do their job of operating the system identified as solutions. And then here is just a list of solutions that have been developed to be able to operate a power system with high amounts of renewables. Maybe it's good to make a stop here and to think that we have talked, or I have talked a lot about challenges and changes. But the fact that I can talk about challenges and changes means that these things have been studied and have been understood. So we more or less understood what is different and what is difficult with renewables. So it means that we are also in place to develop solutions. And this is why we are able right now to operate systems with the amounts of wind and solar power that we have. And here is just a list of these solutions that have arisen after carefully analyzing my system and the challenges with the changes that the renewable energy has brought. So one thing is to obligate the renewable energies or the variable renewables to behave similarly in the way they support the power system as the conventional generation. And this is when people talk about grid code and grid code connection. So those are conditions that I put to the wind turbines and to the PV systems so that they behave friendly and good with the grid. Other thing is to make my transmission network stronger, to be able to trade electricity, but also to be more robust to any failure that may happen in the system. Interconnection with neighbor systems to smooth the power. This also applies for this shorter term, flexible conventional generation we were talking about. Storage, so being able to develop or to store electricity, not to rely only on this instantaneous production or instantaneous consumption, and relying more on demand-side management, which means relying more on the customers. So not only giving the responsibility of the generators conventional generators to go up and go down whenever the wind starts to blow or stops to blow. Also, consumers can help to maintain this balance. Increase the accuracy of the forecast to make the production of the wind and the sun more predictable, and then to plan it better, and all this thing of measuring and being able to monitor and to know how the system behaves, that is the smart grids, and always looking forward for new innovative solutions, as mentioned before. So we're still not able to operate whole Europe only with wind, but this is the direction things are taking, and as Daniel mentioned before, we need to do something to achieve these targets, so we need to put more renewables into the grid, so we need to develop new solutions, and this is not static, so this is changing, and there's a lot to do there. And I don't know, like the German government invests every year considerable amounts of money in research and develop to find the best ways to clear the path, so to have more renewables. And all this has an impact on the way the people that operates the system solves the challenges that can arise with the renewable. Here is just to conclude this part. So this is a picture of a control center. This is the people that is like in the real time making sure that we have lights. But behind these people, here is like the process. Here is where these people is sitting. Then there is a long and very complex process of planning. So from this strategic long-term planning to planning how the system and how much energy I will have in 3 years, how I will schedule the maintenance of my grid and of my generators for the next year, to planning how much every generator is going to produce tomorrow. All this is this planning process that I was mentioning before is like the schedule of the people in the airport controlling the traffic of the airplanes. So they are doing the live job, but there's a big, enormous effort before that. And now with these physical changes that we introduced with the renewables, this process has been adapted and is being adapted and is changing and is evolving. And in this environment, so besides like the long-term planning work, so in IRENA, with a team that we call Power System Transformation Team, which includes not only Asami or myself, but also other colleagues, Emanuele, which is here, and Carlos. We try to support countries in all these aspects of planning. So from this strategic long-term to the more daily and mundane issues of being able to keep the lights on when incorporating a lot of renewables. And let's say that for doing this, maybe our support or a specific country support is more in smaller countries, developing countries, where there is still a long way to go. And what we use is that we try to learn as much as we can from countries like Germany or Spain that have already the experience. And this is just a map of countries where we have been engaged. I particularly work like in the shorter term issues like this stability and this grid planning. And the first countries where we started to work were the small island countries, like the islands in the Pacific and the islands in the Caribbean. And it has a reason, and it's because those systems are smaller, they are less robust, and then they have this issue with the stability and with the frequency stability. And they were the first one that started to question about this. They are really strongly affected by the climate change, and they want to use renewables, and they will benefit a lot of not importing fuels. But then the people in charge of the electricity were questioning a lot. Yeah, but what do we do with our system? Are we going to be able to keep the lights on? And then we have, since 4 years, starting a program to support these countries. So let's say, first focus was Pacific island countries, Caribbean island countries, and we have started to grow and to grow work in larger systems still on developing countries, so in Central America and in larger islands like Cuba or Dominican Republic in the Caribbean. And to do this, we have learned a lot from German, from Europe, or from the US. And yeah, I guess this is all what I wanted to say. I don't know if there are any more questions or if you want to discuss further, not only for myself, but also for Daniel. Welcome. Yep.
Sorry, I have a question regarding to the goal of the long-term planning, as you mentioned before, or Daniel Bush mentioned before. Because, for example, you mentioned on the slide 34 that the goal is to maximize the integration of renewable energies. And I think that the main goal is to reduce the emission, and the renewable energies are a solution to this problem. That is not clear for me.
So if I could repeat your question, just to get it on the recording, you're saying, so it's one of the slides where we had the goal of power sector planning, is that right?
Yeah.
That was this slide. Is it further back?
34.
Okay.
It's not a matter of the thing is, I try to understand. The main goal is here to obtain the optimal integration of renewable energies, or the main goal is to reduce emissions in the long term.
So the question is, for if anyone couldn't hear, is the goal to reduce emissions or increase the amount of renewable energy? Something like this?
Yeah.
In an optimal way. And I think you take it in two different levels, perhaps. The overall goal, of course, is to reduce the emissions. This is the first step, and you take that in the different sectors of the energy system. So the power sector, the heating sector, and the transport sector. And part of the solution to reduce the emissions is to optimally introduce renewable energy into the power system. And this is kind of depending on the institutional setup of a country. Sometimes they take these two goals together at the same time, and they'll look at the energy system development and reducing emissions overall in the energy system first, and then they'll look specifically at the power system, or they could look at these two things together. Typically, you have to kind of take everything all together at once in the planning process. I don't know if that answers. Yeah.
Also, the sector coupling is considered in the plan.
And so this question is, do we consider things like sector coupling, which is a term which basically means taking power generated in the power system by renewables or gas or coal and using it for other sectors. So something like transport or heating. For example, electric vehicles will use a lot of power generated by the power system, which currently isn't the case. And this is probably something that's the most interesting topic that people are discussing now. The models that people have been using haven't always taken this into account. So there's an entire group of people all over the world, that's academics and researchers, who are trying to incorporate the coupling of different sectors together. And how do you optimize your use of energy, not just to provide electricity to us, but to also provide electricity to cars, to buses, and perhaps even to heating networks, things like this. So this is something that we look at IRENA. We're just starting to look at this. And a lot of the advanced countries are thinking about it too. If there are no more questions, maybe we can just say thank you again for taking the time out to come here.